Hi, I'm Clover May. I'm currently a postdoc in the math department at UCLA. I work in algebraic topology, mainly equivariant homotopy theory. And at UCLA, my postdoc mentor is Mike Hill. Before that, I earned my PhD at the University of Oregon, where my advisor was Dan Duggar. The bulk of my work is in ROG-graded cohomology, where I use computations to inform theory. So for Geofinite Group, the spaces I'm interested in are G-CW complexes. These are CW complexes with a cellular action by the group G. And in this equivariant world, there are all kinds of interesting spheres. So for example, if you take a real representation, you can one-point compactify and get an induced action on a sphere. This equivariant cohomology theory takes into account these representation spheres in the sense that it has a nice suspension isomorphism with respect to them. And that makes this cohomology graded on the real representation ring, ROG. For G equals C2, the cyclic group of order 2, that's a bi-graded theory because of the trivial representation and the sign representation. So we write HPQ of a C2 space X, where P is the dimension and Q is the number of sign representations. And if we work in the equivariant analog of coefficients with the field F2, then we get an ordinary equivariant cohomology theory, and it's represented by a genuine equivariant Eilenberg-MacLane spectrum, HF2. Unfortunately, even though this is the analog of working with coefficients in a field, computations here are quite challenging. Even the cohomology of a point is quite complicated. So here's a picture of M2, the bi-graded cohomology of a point as a C2 space. We see these two cones, and every lattice point inside these cones represents a copy of F2. The top cone is polynomial in tau and rho, and the bottom cone has a class theta that's infinitely divisible by tau and rho. This makes M2, the cohomology of a point, an infinite dimensional non-Noetherian ring. Now, the cohomology of every C2 space is a module over this ring, but that means we have to consider modules over a non-Noetherian ring. And these can be quite complicated. As an example, here's the cohomology of the sphere with the antipodal action. We see this vertical strip with a bunch of copies of F2. The vertical lines here represent multiplication by tau, and the diagonal lines represent multiplication by rho. This is just one example. There are many complicated M2 modules. And computations here are quite complicated because of that. However, in my thesis, I proved that in the cohomology of a C2 space, you don't see too many complicated modules. So for X, a finite C2-CW complex, to describe its bi-graded cohomology, you only need two types of summands. M2, the cohomology of a point with these two cones, and the cohomology of the antipodal sphere, these vertical strips. All other kinds of M2 modules don't show up in the cohomology. This is really surprising because, again, there are so many strange M2 modules, and also that this is not true for C3 spaces, for example. So in ongoing work, I'm interested in describing the summands required for the cohomology of C3 spaces in F3 coefficients, but it is significantly more complicated. In the C2 world, I've lifted this to a statement at the spectrum level. So we actually have a splitting of spectra. If you take Y, a finite C2-CW spectrum, and you smash it with the Eilenberg-MacLane spectrum, then it splits as a wedge, and that wedge has only two types of summands. Again, there's HF2, the Eilenberg-MacLane spectrum, that corresponds to M2, and of course, a piece corresponding to the cohomology of the antipodal sphere. You might hope that this would give a complete classification of compact HF2 modules, and unfortunately, that's a bit more complicated. But in work in progress with Dan Duggar and Christy Hazel, we describe a complete classification here. This uses very different techniques, but we find that if we have a compact HF2 module, then there are only three types of summands that we need. Again, the two we had before, HF2 and the antipodal sphere. The last piece we need are cofibers of powers of tau, where tau was that element in M2, the cohomology of a point. We also go on to describe the Balmer spectrum, or the tensor triangular spectrum, in this category. In future work, we're interested in varying the group, considering C3 or CP for odd primes, as well as varying the coefficients. For example, integral coefficients would be very interesting. Another thread of my work is looking at commutative equivariant ring spectra. This work is collaboration with Anna Marie Bowman, Christy Hazel, Jocelyn Ishak, and Magdalena Kedzorek. In this work, we let G be any finite abelian group, and we consider algebraic models for rational equivariant ring spectra. Now, there are a number of different kinds of models because there are different levels of commutativity in the equivariant world. You might have naive E-infinity commutativity, or you might have the best kind, genuine commutativity, with all the norms. In this work, we computed the image of equivariant complex K-theory, KU, and through that computation, proved the following result, that in fact, KU admits a unique structure as a naive commutative ring. In ongoing work in progress, we consider KU in another algebraic model and show that, in fact, KU admits a unique structure as a genuine commutative ring. In future work, we're interested in considering other important spectra, such as Atiyah's real K-theory and complex cobordism, MU. Thank you for your time.